Hi there, my name is Justin, and I'm a research scientist in the core systems team at Facebook. And today I'll be discussing Maelstrom, a system we use to mitigate data center level disasters. These types of disasters can take many different forms, such as hurricanes. For example, last month when Hurricane Florence was hurtling toward our Forest City data center, we used Maelstrom to redirect production traffic away from Forest City and to other data centers. The process was mostly automated, redirected most traffic in tens of minutes, and resulted in no user impact. But this is not how things always were, even a few years ago. Take Hurricane Sandy in 2012, for instance. For Facebook, Hurricane Sandy was a wake-up call. Sandy came within 30 miles of our leased data center and narrowly avoided our Forest City data center. If Sandy had hit either of these, Facebook would have gone down. This is especially problematic for us because during disasters, people use our services to coordinate response efforts and make sure friends and family are safe. Fortunately, Facebook was fine, but we asked, can we run Facebook without one of our data centers? This question may seem simple, but it's really hard to answer correctly, especially because each of our data centers is massive, with many thousands of servers, hundreds of software systems, and consuming enough power for a city of people. But quick show of hands, how many of you have been in a hurricane before? Okay, so a few here and there. Now, how many of you have ever had a bug in your code? Put those hands up. Now picture that bug gets deployed across an entire data center and causes a bunch of servers to start crashing. That disaster hits a bit closer to home. So whether it's natural or human-made, we need a strategy for draining our data centers for disasters. To do this, we had to think about data center fault tolerance in a structured way. And if there's one thing you take away from this talk, it should be these 3 points. What we had to teach ourselves was that correctness, how people expect our site to operate, dictates the design space for fault tolerance techniques. And preserving correctness requires tracking dependencies between microservices and carefully redirecting traffic in the correct order. Finally, making sure that everything works when you need it to requires continual testing. If you ever work on data center level reliability, you'll inevitably have to deal with these yourself. But in this talk, I'll tell you about the path that we took. Starting at the very beginning, this was the first version of how we dealt with disasters. Let me introduce you to 2 concepts that you'll hear about in this talk that are common at Facebook. Draining is what we call redirecting traffic from one data center to another, and runbooks, such as this whiteboard, capture the drain plan. Once we had a runbook for draining data centers, we used war rooms and spreadsheets to coordinate the work of our engineering teams to manually drain data centers. We quickly learned that manual operation is error-prone, as many people make mistakes when they're tired or stressed. So we started working on Maelstrom to automate the steps needed to drain a Facebook data center. And as you see in this Gantt chart, track their performance. This work allowed us to dramatically improve efficiency and decrease errors. To recap, I've motivated the need for draining data centers safely and introduced Maelstrom, the system we've built at Facebook for doing so. Here's the roadmap for the rest of this talk. In order to understand what happens in our data centers and how we respond, I first need to describe what goes on in a Facebook data center. Then, I'll discuss how we empowered humans to do the operations of draining a data center safely and reliably by automating most of the process. Finally, I'll discuss how we use Maelstrom to run regular tests and present results captured from draining our Forest City data center for Hurricane Florence. So let's start by taking a look at what happens when I click on a post in Facebook. First, a request is sent to a web server in one of Facebook's data centers around the world. And while what goes on inside a Facebook data center may seem like a black box, it's really no mystery to all of us. For example, at Facebook, we don't build huge monolithic systems. We build modular microservices and compose them. In fact, you'd find many similar systems to the ones we've all built, the ones we've been talking about, and the ones from past OSDIs and SOSPs, all running alongside one another. But when you compose modular systems together, you end up with a problem: dependencies. And for correct and safe drains, we need to drain systems gracefully, based on their dependencies. For example, you can't just start draining cache servers, because then the web servers will send a thundering herd of requests to the database servers, overloading them. So how do we drain data centers safely and efficiently? Well, a prerequisite to doing that is being able to manage all of the traffic at Facebook. We classify traffic into 4 categories, with a different mitigation strategy for each. For example, a web server is stateless. You can take one web request and have it served on any web server in a data center. A database server, on the other hand, is stateful. The server can only handle requests for the data that's stored on it. At Facebook, we identify 2 additional types of traffic. For example, a mobile app might want to cache some data server-side, so it might prefer to go to the same server most of the time, but it can rebuild that cache state if it has to get moved. That's sticky traffic. Or a cache service might send traffic that's harder to move around without relaxing consistency. That's replication traffic. With Maelstrom, we've developed a set of patterns for draining these different types of traffic. For example, here's how a stateless traffic shift is encoded. We define a task template that exposes a generic API for draining stateless services. Note that this traffic shift template is implemented in the site load balancer, not in all of the different stateful services, so those don't require code changes. We collect tasks into runbooks, where Maelstrom executes them according to each task's parameters. I encourage you to read our paper for the other traffic type templates. Now, in order to help a site operator guarantee safe execution, however, we need 3 new primitives. With Maelstrom, we combine dependence, automation, and validation to ensure safety and efficiency. Let's discuss each of these. Starting with dependence. Maelstrom incorporates dependence information among different services to ensure that we can drain them safely. This is encoded as a directed acyclic graph, and it's constructed through observation and testing. And here's an example of a simple dependence graph expressed in a Maelstrom runbook. Each of the nodes is an individual task involved in draining a Facebook data center. Now, this dependence information plays a really important role, because the actual dependencies to drain Facebook gracefully are quite complex. This is what it really looks like when we drain a data center at Facebook's scale. Over time, our goal is to reduce the complexity of this graph so that we can respond to disasters even faster and more efficiently. Another thing that's helped us reduce manual error when draining a data center is our extensive use of automation. We've automated things from shifting traffic to manipulating jobs, changing configurations, and moving shards around. We also want to move fast while draining a data center, and validation is what lets us do so safely. With validation, we define metrics and thresholds to track service health. It determines when we can launch a step, and also determines when different steps have completed. We incorporate these with various service health checks to make sure that the site is remaining healthy. So we had dependence, automation, and validation to help a human drain a data center. Now, this greatly improved the repeatability of our drains, but humans are slow and non-deterministic. So we tied everything together with a scheduler. Let's take a look at Maelstrom's end-to-end system architecture. We use a tool called the Runbook UI to interact with a MySQL database that stores a runbook's data. Dependencies between tasks, metadata such as notes, and even the task definitions themselves. All communication occurs over Thrift remote procedure calls. Drain execution is initiated via the Runbook UI. A Python service called the scheduler reads a runbook to execute from the database and updates the database with the status of tasks being executed. The scheduler also monitors health checks associated with the tasks, using metadata that's embedded in the runbook to determine when it's safe to execute a task. When the scheduler deems a task ready to execute, it sends a request to the executor. Like the scheduler, the executor is a Python-based Thrift service. Tasks are implemented using a well-defined API and cover the range of things I talked about, like shifting traffic and changing configs. And here's what Maelstrom looks like in action during a recent drain test. This is the runbook UI, and we've just sent a request to the scheduler to drain a region. Each of the rows represents a task and contains some metadata for dependence, automation, and validation. You'll see that the scheduler begins to pick up tasks and transition them to the ready state shown in purple. And when they're sent to the executor, they turn blue. Tasks that are done are shown in green. Each step has a green button that allows us to manually step in and override the automation if we need to, and 2 columns that represent different health checks that are being performed to determine when it's safe to start the task and when it's completed. Now, behind the scenes, the scheduler actually executes the runbook according to its dependence information, and all of these steps follow that dependence chain. We do weekly drain tests with Maelstrom, where we drain one of our data centers. All these tests do is just make sure that the dependencies are valid and that our tools work. Now, Maelstrom has several limitations. For example, we must plan out how shared resources such as network bandwidth will be used when a data center is drained. In addition, Maelstrom is a reactive approach to disaster mitigation that works best when you have time to plan, although we also use Maelstrom to minimize the downtime associated with instantaneous failures. Finally, Maelstrom is not always the fastest way to mitigate a disaster. Oftentimes, reverting a bad release or patching a fix forward can take less time. So to tie everything together, let's go back to Hurricane Florence. I'd like to walk you through our runbook for this type of disaster. We start by draining stateless traffic. I'm showing one particular service for ads that has around 2/3 of its traffic from users and 1/3 of its traffic from internal services, which we drain in a later step. We control stateless traffic using a multiplier value shown on the left y-axis. And this multiplier value is stored in our site load balancer. The multiplier value just changes the amount of traffic sent from users to a given data center. On the x-axis, we have time before Hurricane Florence, and you can see that as we change the multiplier value of traffic sent from users to this data center from 1 to 0, that corresponding 2/3 of traffic decreases as well. And then we show in blue on the right y-axis the amount of requests per second. After we've drained stateless traffic, we next drain sticky traffic. This is a page rendering service for feature phones. Notice that decreasing the multiplier value, shown in red again on the left y-axis, doesn't immediately drain the sticky traffic. It only stops new sessions from going into the data center. In order to actually drain the sticky traffic, we have to evict the existing sessions. Now, this is a really good example of a dependence that we encode in Maelstrom. First, we need to stop the incoming connections from going to the data center, and then we need to start evicting the existing connections. So Maelstrom handles this sequencing for us. And you can see that by the end of that hour at 9 a.m., we've evicted all of the active sessions from our Forest City data center. Finally, after draining sticky traffic, we drain stateful traffic. In this case, we used Maelstrom to coordinate the drain of data shards in a large-scale distributed data store, something that the Accio paper that you'll hear about later in the day is built on top of. The jumps in this graph correspond to different data sets, and some data sets are only used within the data center being drained, not outside of it. So there's no need to actually drain those. That's why we have a bit of residual traffic still going to the data, residual primary shards still going to the data center at the end. Okay, so to conclude, when you compose modular microservices in a data center, you introduce fundamental dependencies. And for correct and safe drains to mitigate data center level disasters, you need to be able to detect and use these dependencies to your advantage. For highly dynamic systems, the ordering and specific parameters used to drain a data center changes all the time. And so you have to follow this procedure up with verification and testing to make sure that you can always drain when you need to. Thank you, and I'd be happy to take any questions.
Marcos Aguilera, VMware Research. I'm wondering, don't you have mechanisms to deal with an instantaneous failures of everything, like lightning strikes and 2 microseconds burns everything? And if you have something to deal with that, why do you need to drain stuff?
That's a really excellent question. It turns out that dealing with those very fast instantaneous failures is incredibly challenging, especially when you're, say, writing different consistency data or other things like that. We do have some systems at Facebook that can operate at the sort of millisecond scale to be able to handle power spikes or different events like that. The problem is this type of reactive service is not deployed across all of the different hundreds of systems at Facebook. And so while we have this for maybe key critical services, we still need something that ties everything together.
Thank you.
Yeah.
Rich Draves, Microsoft. So I guess I was going to ask the same question as Marcos, but let me just make sure I understand your answer. So you're basically saying if a Facebook data center goes down abruptly, that will cause an outage for Facebook.
Yes, and our best mitigation plan is to use Maelstrom to drain traffic as quickly as we can.
Okay.
So Suli from Ant Financial. So I'm just curious, how do you get those dependencies? And they sound like really hard to maintain.
Yes, and actually I want to go quickly back to the previous question. For something like a lightning strike where it's a power failure, we do have backup generators and things like that. But again, those only operate for a limited amount of time, so we're going to need to drain traffic as soon as possible. In terms of how we determine and curate dependencies, that's a really awesome question as well. So a lot of when we first started out, when I showed you the whiteboard picture, a lot of it was just kind of like sitting down, doing pen and paper, trying to understand the systems. These days, we have that dependence graph that we've curated, and the way that we determine new dependencies or whether dependencies can be broken is through our regular testing. So for example, we might go to drain a service and notice that another service becomes unhealthy. This implies that that service might have to take a dependence, and so we'll add that into our dependence graph.
Do you think it's a little bit costly?
It's a really good question. One of the things that we're trying to do now is figure out ways to sort of automate this procedure so that we can do this a bit more efficiently. But for right now, given that the technique is driven by humans with the help of this automated scheduler, it kind of fits our workflow.
Thank you.
Yeah.
Hi, John Osterhout from Stanford. I think I'm kind of repeating the previous questions, but I'm still trying to wrap my mind around this. Are you saying that geo-replication simply doesn't solve the problem and we need other things? Or is it that you didn't fully implement geo-replication or didn't get it right in, so then you had to have the draining to make up for its weaknesses?
No, actually, geo-replication is one of the mechanisms that enables us to do this type of draining. So for example, for the data shards case that I showed, each of those shards is just a primary. We actually have secondaries in other regions. And what enables us to kind of quickly flip the switch and start redirecting users to other data centers is the fact that we have geo-replication in multiple data centers going on. Does that answer your question?
I thought the whole idea of geo-replication is that was all you need to handle cases where data centers go down. But you're saying that's not enough.
So in practice, the load balancers that we have are not going to be able to necessarily detect and figure out all the right dependencies for how to fail over user traffic gracefully to take advantage of those geo-replicated data. So we actually need something to tie together all of these different systems. Geo-replication kind of provides the framework that we need to get this all right, but we need to make sure that there's something that's actually handling these dependencies and failing over traffic gracefully. Thank you.